Good morning, ladies and gentlemen. My name is Zhang. I'm a postgraduate student from Beihang University. And today my topic is a miniature fiber optic photoacoustic probe coated with molybdenum disulfide PDMS for water level and oil-water interface detection. And here are the contents. We know there are various liquid level sensors, optical ones, ultrasonic ones. And here are two examples of optical liquid level sensors. The first one, sublicing a single mode fiber with a multi-mode fiber, and the second one, sublicing a single mode fiber with a no core fiber. These optical fiber sensors, they are immune to electromagnetic interference, and which is a good point, but they also have some disadvantages, like they are the manufacturing process is complex, and they can be they have a relatively small measurement range. And on the upper right, there are two types of ultrasonic liquid level sensors. They have lower cost compared to the optical ones, but piezoelectric ultrasound sensors are sometimes difficult to manufacture. And here, on the lower side is an example of photoacoustic liquid level sensor. We input a pulsed laser, and the light absorbing material absorb the energy of the pulsed laser and generate ultrasound. This kind of photoacoustic sensor has both the advantages of optical ones and ultrasonic ones. So here is what I do. First, I introduce the sensor fabrication. Take a fiber and a ceramic ferrule and cleave the end face of the fiber and insert the fiber into the ferrule. Then stick them with epoxy adhesive. Then use these two things to dip into a molybdenum disulfide solution and take it out until the solvent evaporate several times after the layer reaches a certain level of thickness. Then deposit the mixture of PDMS on the end face and put it in a drying oven for about 60 degrees Celsius for about an hour until it cured. And here is the picture of the sensor. And these two pictures are taken under microscopes. And for ultrasonic sensors, I want to explain the measurement principle. First, we need to know the sound of speed in water or silicone oil, which are the two liquids I use. Here is H is measured by meter ruler, and T is measured by oscilloscope, and use this equation to calculate the sound speed. And for water level measurement, I need to know the first time the PZT detects the absolute time the PZT detect the ultrasound signal for the first time and the second time, and calculate the time difference and times the sound of speed in water, and half of it is this height, the water-air interface to the distance between the water-air interface to the PZT surface. And for oil-water interface, I use H3 as the what we call the oil-water interface level, and measure H1 and H2 using a meter ruler, and then using this equation to solve H3 in condition that Vs and Vw, which are the sound of speeds, known. And this T is the ultrasound travels, this length, the time of this length. And here are the experimental setups. We insert the PA probe and the PZT into an acrylic glass tube, and here is the cube, and use a PC to generate control signal to pulsed laser and YDFA. Ytterbium doped fiber amplifier. And there's a coupler to connect the pulsed laser, YDFA, and variable optical attenuator. The signal generated by YDFA is sent into the probe and generate ultrasound and detect, and the signal is sent to preamplifier and then oscilloscope, and this laser signal is detected by photodetector and then oscilloscope, then data is acquired by the PC. And here are some key parameters of the devices, in case anyone wonders. Then here are the experimental results. Well, here, the red line is trigger signal. The black line is the received signal. Peak A is the laser peak, and peak B is the photothermal peak induced by the direct exposure of laser on the PCT surface. And peak C is the peak of the ultrasound. And this is a spectrogram of the ultrasound signal. We can see that the -6 decibel bandwidth is approximately 13.3 megahertz. Then this is the water level detection experiment, and here is the experiment setup, and here are the results. I can record the time of the first wave and second waves, and these are the enlarged figure of the second waves. As I add water into the tube, as the water volume increases, the peak has right shifts. And then calculate the water level. Well, the water volume is calculated by every time I add some water, and then I calculate the volume. Then the measured liquid level are here, and then I make a linear fit, and the R square is 0.9964. And here is the setup of the oil-water interface detection. Immerse the PCT and the PA probe into the oil layer, but do not touch the surface. Then add water through this tube. Then the water level rises, and as the water level increases, the second wave has left shifts. Then this is the demodulated water level interface, oil-water interface level, and the reference liquid level is measured by a meter ruler. And here are a linear fit. The R square is 0.9871. So here are the conclusions. Some main parameters. This is 13.3, and this is 8.82 micron, which is corresponding height of a volume of 2.5 microliter. And the R square is that, and relative error is 0.027%. For oil water interface level detection, R square is 0.988, and relative error is 0.68%. And that's all of my report. And questions?
Thank you.